Hey, let's learn some more about Venn diagrams. We're going to learn the difference between a subset and a proper subset. Also, we're going to be listing sets, which we've done before, but also illustrating these lists of elements in a diagram. First, I want to show you the definition of a set that looks just a little bit different from what we've seen before. This is sort of what we've seen before, where like the definition of the set is inside the squiggly brackets, say the set factors of 10, and then we could list them. Or this definition, a set positive odd numbers, and then we could list the set. You may run into definitions of sets that look like this. The way you would read this is to say D is the set of numbers x for which x is an even number, or where x is an even number. So D is a set of numbers x where x is an even number. Then we could list the set, of course, and just say D apparently is 2, 4, 6, 8, and so on, right? Here, this is kind of cool. We have a list of coordinates now, coordinates x and y. F is the set of coordinates where y is always equal to x plus 2. So really, F is the set of coordinates that fall on this line, right? And if we wanted to list those coordinates, then we would make a table of values for our line. Say if we plug in 0 for x, y will be 2. If we plug in 1 for x, y will be 3. If we plug in 2, y will be 4. And then we can list our coordinates. Don't forget to separate them with commas, right? And so on, because the line actually goes on in the negative direction as well. Sorry. Right, so you could run into definitions of sets that look like that, just so you're familiar with those. Then I want to tell you the difference between subsets and proper subsets. Let's look at this. A is a set with 3 elements, 2, 4, and 6. B is a set of elements that are exactly the same. Also 3 elements, 2, 4, and 6. Here we could say A is a subset of B. We would write it like this. A is a subset of B. We would draw it on a Venn diagram like this. There's a set B, and all of the elements that are inside set A are also part of set B. And there is even nothing inside B that is not also in A. So when this is true, it is always also automatically true that B is a subset of A, right? Because there's no elements inside A that aren't in B. There's no elements in B that aren't in A. So we could also say it like this. But here we would say B is a subset of A. If this is not true, if something is not a subset of something else, we just write A is a subset of B and then cross out the is a subset of sign, right? Okay, now let's look at this second example. Say our set A has the elements 4 and 6. Our set B has the elements 2, 4, and 6. And as you can see, all of A's elements are also part of B, but B has one element that is not inside A. We call this a proper subset. Proper subset. A is now a proper subset of B. That means that all the elements that are inside A are also inside B, but there must be at least one element in B that is not part of A. And we would, again, A falls within B, right? But there's at least one element that is in B but not in A. So if we were to write the elements inside the circles, we would have inside A, we would have 4 and 6. And inside B, but outside of A, we have the 2. And if we were to do that on this side here, we could write all the elements inside A. They automatically also all fall into B, but there's nothing inside B that isn't in A, right? See the difference? The way we write this is A is a proper subset of B. And if we wanted to say that this is not true, we would say A is not a proper subset of B, right? Okay, the fun part. Let's look at this. There's a universal set, so a set of elements that we're considering. It's all the numbers up to 10. There's a set A, which is the even numbers smaller than 10. B, multiples of 3 smaller than 10. There's a set C, which is the prime numbers under 10. Okay, these all fall within our universal set, right? We could, just for fun, before we make this diagram look nice, we could ask ourselves to list the complement of A. Let's see if we can do that. So the complement of A is all the elements that are not part of A, but still inside our universal set of elements that we're considering, right? So we just list all the elements that are in our universal set, but not inside A. So that would be obviously all the odd numbers plus the 10, right? Okay, and we could make all sorts of lists, like the union between A and B, or the intersection between A prime and C, or whatever. The cool thing is that we can illustrate all of this green information here in a Venn diagram, which would mean we write in all the values, all the elements in the correct parts of the circle or outside of the circle. Let's start by writing the elements of A inside the circle A, but we have to be careful because the 2 that's in A also has to be in C, but not in D. So that would be right here, right? The 4 is only in A, 4. The 6 is inside A and B, so I write it here. The 8 only appears in A, so right there. Let's move on to set B. I have a 3. The 3 also appears in C. The 6 is already there. The 9 doesn't appear in C, doesn't appear in A, so that's just right there. Let's see if there's anything left in C that we haven't already written in there. The 2 and the 3 are there already. The 5 doesn't fall into anything else. We already know that actually. The 7 didn't go in A or B, so it only goes into C. And we're not done yet because we have our universal set, and some of these elements that we were considering didn't fall into either one of these three sets, right? We have the 1, it's not an A, B, or C, so it goes outside. 2, 3, 4, 5, 6, 7, 8, 9. The 10 also falls outside of the 3 bubbles, right? And then in the next lesson, we're going to do even cooler stuff with diagrams like this. So I'm looking forward to that. I'll see you soon.